hear me? Oh, yes. Okay, hi. So this is ReVault and how you can get compromised by your secure system on chip. So hi, I'm Philippe Laulheret. I'm a senior vulnerability researcher at Cisco Talos. And I focus on Windows, embedded systems, and basically what we do is we do third-party, like my team at least, we do third-party research. We find vulnerabilities, we report them to the vendors. Hopefully they fix it, and then we disclose our findings with like blogs and presentations and that kind of things. And so like I did that work, that project for work, and here it is. So what can you expect from this presentation? So it's going to be a 40-ish minute talk, where I'm going to go over some bugs that I've reported to Dell and Broadcom earlier this year that lead to like a full compromise of something called Control Vault. And so we're going to see what that is. So here is like, the laptop, nothing too crazy, but here you have a fingerprint reader, like an NFC card reader, and on the side you have a smart card readers, and all of that are like peripherals that interact with that thing called Control Vault. And if you open the system, the device manager, you can see this mysterious thing called Control Vault device. And I was like, okay, what is that? It's interesting. If you open the laptop, remove the battery, you can find the Control Vault device in there. So that's this board, and it connects to the motherboard over here. And here you can just see like a little like flash chip that sticks out, and that's all. And all of the other peripherals are connected to it on the side, Okay, so now you can be like, what is Control Vault? And that's kind of the question I was asking myself when I started this project. So this is technically Control Vault 3, and it can be found in like over like 100 different models of Dell laptops, mostly like the business ones, so Latitude and Precisions, and you can see the board here. It's a mix of like software, firmware, hardware, so you have like Windows APIs or potentially Linux API as well. It runs its own firmware, like on this chip here, which is a Broadcom BCM58202. And so the firmware is a real-time OS running on that like ARM chip. Technically, it's also like a secure storage of secrets. And so here you have like a flash that's encrypted and meant to be secure. The whole board is called Unified Secure Hub, and that's because you can connect all of the security peripherals I was mentioning earlier. That's Control Vault 3. Now there's also Control Vault 3 Plus, which you find in Dell Pro's laptops. And the findings affect both equally. And before that, you also had Control Vault 1 and 2. Control Vault 1 was like 2010. Control Vault 2, I don't remember, and Control Vault 3 was like 2019. And just for Control Vault 3 and 3 Plus, that's probably like in the tens of millions of devices that should have that. But that being said, some of the findings I found were like also in Control Vault 1, or at least from reversing it looks like it, because I didn't find like an all laptop to verify that, but the firmware looked like it was vulnerable. So some of those bugs are probably like 15 plus year old, which is pretty cool. And there is no documentation, so we have to do some digging to figure out like how the thing works. And for that, step one is to Google stuff. And something really useful is this repo here, which is the host side APIs for Linux. And what's interesting there is that it's compiled with debug symbols. So if you import the file in IDA, you will get a lot of structures, enums, and all of that is shared with the firmware itself. So that's a good insight of data structure to be found in the system. So it's really useful for reversing. And then there is this file, which is some like certification about the system on chip itself. It has like a cryptography module, and that's the certification for that. It doesn't give much information. It just give a hint of the way the system works, but also like explain some acronyms in the that might be found in firmware and stuff. Like for instance, here you have that thing called SBI for secure boot image, and which is like an extension of the boot ROM of the system on chip. So it might be useful later, we'll see. And so now it could be like, why did you target that? Beyond the fact that there's 10 millions of devices that could be affected by it. The beginning of the whole research project was much more humble. I was looking, on one of the system I had, stuff that were running on my machine, and that thing caught my attention. I was looking at which binaries are running without ASLR enabled, and clearly like there is a glaring missing part here of something running a system, which is not great, you know. And same here, like the DLL that are imported by those stuff also don't have ASLR, and all of that is the Broadcom, you know, control vault stuff. So I was really getting excited, you know. I was like yelling from my window, you know. I was like ready to like hack stuff, you know. And yeah, what's the next step on that project was just start digging deeper and basically extracting files from the installer to see like what is all the stuff that make control vault. And turns out there is so many stuff. There's like a driver for the USB stack, the fingerprint reader stack, the smart card, the NFC, so much stuff. There's like Windows services and DLLs that nobody uses. I have no idea why they're there. And there is a firmware folder that's really got me excited. In particular, like there is that, you know, SBI thing that I was just mentioning that's in clear text. So like, you know, you can import that in IDA if you're curious. And then there's like one called like Citadel that is the application firmware, like the real thing that, you know, we would normally talk with. But that one is encrypted. So, you know, it's like, are we going to have to figure out how to decrypt it, you know? But before we go too far, to give an idea of the system architecture of the whole thing, so here you have the firmware, right? On the left side, you have like all the hardware stack, and it's talking with the firmware with like various like, you know, embedded buses. And on the right side, you have the host, talks over USB. So the ribbon cable that connects to the motherboard is like basically like internal USB. And on Windows, you're going to have like a USB driver here that, you know, connects with the thing. And user land, you have some control vault APIs that feeds into different services and, you know, various like user land drivers. So that's the idea. But yeah, so if we want to talk with the firmware, the way it works is the driver, the USB driver, is going to create like a device on Windows side, and user land can open that device and send a device IO control to it, and eventually that will be turned into USB packets that are sent to the firmware. But that's a pain in the ass to you know, do all of that manually. So, you know, Broadcom made you know, DLLs that implements all like high-level functions. And so those functions are like called like CV commands. You have CV open, CV close, create object, get object, etc. Like there's like 150 of them or something. So it's tons. And yeah, most of those functions expect a handle that will be obtained using CV open first. And on the firmware side, you know, you have like the dependent of that, where you have a CV manager command that's kind of a dispatcher that when it receives a CV command will, you know, invoke the appropriate functions. And all of that is obviously like a huge attack surface, you know, because as I said, it's like 150 commands, so there's a lot that could go wrong. But, you know, before we start messing too much with it, like how we can talk with it as a hacker, here's like a 20-line Python stuff where you just, you know, open the DLL that implement all of those commands. You just, you know, tell Python how to, you know, pass the proper arguments, and you could figure that out by, you know, importing the dwarf version, the Linux version into IDA, get exactly like what kind of parameter it expects, and then you can, you know, load the thing on Windows the same way. And then you just call the function. In that case, the command would be cv get USH version. And when you run that, boom, you get like a version string straight out from the board. So with like 20 lines of Python, you can start communicating with that device that's, you know, inside your laptop that you didn't know even existed until like 9 minutes ago. Okay, so we know how to talk with the device, but now how can we target it, right? So attack surface-wise, I can see roughly like 4 areas of interest. The first one is the firmware stack, you know, the SBI and the application firmware, because, you know, they have a USB stack, they process CV commands, and then there is even more stuff for like other Broadcom services that are associated with it. A lot of stuff that, you know, interesting to look at. Then, supposedly, the firmware implements secure boot. So, you know, you should have a secure firmware update mechanism and some signature check. So we want to verify, you know, how well they're doing that. Third attack surface was like the whole Windows stuff. You know, there's like the Windows services that don't have ASLR. You have a driver. Like originally, my goal was just, you know, try to pawn the driver to do like an easy EOP. But, you know, the project become way more. So like all of that is obviously interesting. And finally, like the last attack surface that I didn't touch, but I want to mention is, you know, the whole peripherals. You know, like it's interesting to ask the question, if you have a malicious fingerprint reader, for instance, could it compromise the firmware? Or if you have a malicious firmware, could it compromise the fingerprint reader, for instance? But answering those questions would kind of like 10x the scope of the project, and I was like, okay, don't have time for that. But that's, I think, really a valuable question to ask as well. And just to double down on the secure boot side, this is kind of a simplified diagram, or like the idea I had of how it should look like in the beginning of the project. You have the boot ROM, inside the SoC that's going to verify the secure boot image. And the secure boot image loads something called the secure code descriptor to inform how to start the application firmware. And all of that here is like stuff that you can update. And so you'd expect mechanism to like verify the signature and do proper like update mechanism that's like safe and secure. So it's kind of the idea. We'll have a better diagram later. So, okay, now that we know what we want to attack, like what's going to get in our way, what are the security mitigations. And there's like a few. For the Broadcom services, we've seen there is no ASLR, so we know where like things are loaded in memory. But there is DEP, so you cannot just jump onto the stack. It's not that 2000 like exploitation. So there's like some data execution prevention. But then like stack cookie-wise or stack canary-wise, like it's sometimes are present, sometimes they're not. I'm not sure like which compiler options I picked, but it's And then the control vault firmware itself, something really cool is it does execution in place on the flash while being encrypted. So that's pretty neat. And supposedly, you have a secure boot. But then there is no SLR, there is no stack cookie. So if you can get control of the instruction pointer, you're pretty much done, like if you have a stack overflow. DEP is more questionable because if you try to jump on the stack, it's going to crash. But there's like some read-write execute regions that are mapped. So, well, you can just put your shellcode in there and execute it. So, if you get a stack overflow, it's pretty much game over. Okay. So now that we know how things work, it's time to reverse things. So as a reminder, like the main application is encrypted, but the secure boot image that starts it is not encrypted. So we can try to look at that in IDA and look for like firmware decryption routines or something. And the easy way is like you search for strings, and eventually you can find like pretty sad messages that everything is failed. But the failure of the firmware is our success because that's where the decryption code is. And to give an idea of the process that works, the host, like Windows, in our case, is going to send like an upgrade start command that will provide the firmware header that's encrypted, which will get decrypted by the firmware. And if there is no key present, it's going to use some hard-coded default, which is nice for us because at this point in time we don't have any key. So if you want to decrypt stuff, hopefully the default will work. And then it's going to generate new keys for the execution in place, like the encrypted execution in place. So every time you like update the firmware, it's generate new keys for storing that firmware on the flash. Then you have an update command that just sends like more chunks of encrypted firmware that gets decrypted. To the decryption, it uses some custom IV computation that we'll see in a few slides. And finally, when you're done, it calls an upgrade complete. That's going to verify the whole signature of the firmware. And assuming it works, it's going to commit like remaining data on the flash, and you're good to go. To just give an idea of what it looks like, the upgrade start command, like here is going to load like this default key and default IV. I'm not putting a copy of the keys on the slides because I don't want to get in trouble with Dell and Broadcom. But it gets fed to this USH decrypt function, and you see like the IV here. And the decrypt function uses the key material here that we said just before. And it's just sending like operation to the crypto module of the system on chip. So it's not super clear what encryption mechanism it's using, but from the datasheet we looked at, we may, or not the datasheet, the certification we have, we know which algorithm are supported, and we can just play the guessing game. And it turns out it is, we can just try to decrypt the header, and it turns out like it has CBC, and it's indeed using the default key and IV that we've located. When we decrypt it, and we pick the right algorithm, it looks like that. It's not like completely random data. And just a gotcha is like the firmware tends to swap indenness, so like the byte order for the values, and something to be like aware of. And so that was just the header of the firmware, but now we want to decrypt the whole firmware. And for that, we look at the upgrade command, which is basically just looping over like the blobs of data. And there is that one function that's a little spicy, which is like generating custom IV for the crypto stuff. And I just put it on the slide, so it's easy to, if you want to implement the stuff, you just copy paste that into, Python or Visual Studio or whatever. And the idea is all the math that's being done is just based on the address of the mapping of the address in memory of the chunk of data that you try to decrypt. So when you figure like the base address, the address of the blobs, the blocks of data, and you just feed into that, you get the IV, and you're good. So when you run the whole algorithm, you get something like that. So you decrypt the firmware, you're happy, you can run strings on it, you confirm it works, you find Broadcom strings, it's good. So now we can import the main application into IDA and look for vulns. So that's cool. That's where we wanted to start. So what do we want to do? As I said before, like it implements a lot of CV commands. And most of them expect a session handle that you obtain with like CV open. So it kind of makes sense to start by looking at how it works. So there's a prototype of the CV open command. And on the firmware side, what it does, it starts its malloc, like the session object, write a session tag, so the letter SESS, and then pretty much return the pointer to that session as a handle back to userland. Which, I don't know, to me it's kind of like, sudden, like out of design, it's leaking like address on the heap of the firmware back to userland. It's not necessarily a vulnerability per se, but it's kind of weird, design decision. And then, because we're good, when we open a session, we want to also close it, right? And the way it works, it validates the session. And to validate the session, which is like, take the handle, which is a pointer to the session, just check if the address you're providing is within the heap, look for the session tag, and it's pretty much it. There's a few extra checks that don't matter to us. But yeah, so check that, do you have like the session tag in the proper location, and erase the tag and free the memory. And now, like I know people like to play CTF, and you should have your spidey sense like tickling, because like you really for a session to be valid, you just need to put SESS somewhere on the heap. So with that, I was like, can we do some arbitrary free? Because you just need to put data on the heap. Question is like, can we? Yes, we can. You have a function called CVCreateObject that takes some data and will put it on the heap. So straight out, we can place arbitrary data on the heap, including a fake session. But not everything is perfect. Like the objects have metadata, and we don't control all of that. And also, CVCreateObject return a handle, which is like an actual random number. So we don't know, as opposed to the session that was a pointer. So we don't know where the object is on the heap. But that's not necessarily a problem, because the heap is pretty small, and then we can use a function like, let's say, CVGetRandom, which is just meant to return random data. And what it does is validate the session, and whether or not the session is valid will return different error codes. So what we can do is just try every possible address on the CV heap and ask CVGetRandom, is the session looks valid to you? And if it says yes, you have located your fake session on the heap. So with that, we have like a session oracle to locate fake session that we would try to forge. So just to like summarize that, we have a few cool functions. CreateObject lets you place arbitrary data on the heap. GetObject and setObject that I did not show in the slides, but it's like to read and write those objects, logical. Huh? CVGetRandom lets you locate those objects, and CVClose lets you free session or object that looks like a session. So with all of that, yeah, we have an arbitrary free on the heap. Pretty nice. So now is it like heap exploitation time? that's me when I have to do heap exploitation. You know, like I like CTF, but only so much. So I didn't want to do that. And I was like, okay, what we can do instead is try to find more bugs, you know, because that's also my job, to find as many bugs as I can. And, you know, maybe we'll revisit, you know, how to use this heap vulnerability like later on. And, you know, I keep looking at the firmware, and I found that function called secure bio identify, which doesn't have CV in the name, but is also a CV command that you can reach the same way as before. And that one takes a handle to an object. And what it's going to do is, you know, retrieve the object, and then memcopy part of the properties of that object into this like data2 buffer here. And data2 is just some random stack variable. And so I was like, oh, can I just like immediately do some like, you know, stack overflow on the thing? Because here it's like using the property size to copy the data. And I was like, ooh, am I done already? And not so fast. Like the problem is we need to control the whole field or object value. And actually we don't have that much control. Like we can put some data, but it's going to be limited. So technically there is no like obvious stack overflow there. But you know, we've seen that we can do, we can corrupt the heap. And so we can forge our own object on the heap that would have like the wrong properties to exploit that secure bio identify memcopy. And so the way it would look like, that would be like an object we've created, like here, like on the heap. And we already put the session tag in it. And just for illustration purposes, that's not like one-to-one mapping, but you know, the purple area is like data we can control, and the blue data would be stuff we don't control, like metadata for the object and stuff. But what we can do is create that fake session object, free it using you know, CV clause, and we basically poke a hole inside that object. And then we can allocate a smaller object, and the way the heap allocator works is going to place it inside the hole we've just poked. And what you can see here is that we have some purple that overlap with the blue. So even if we cannot change the metadata of the small object by itself, we can, you know, use the fact that the two objects are overlapping to change the actual, like, you know, data of the large object that will actually change the metadata of the small object. With that, we can place, you know, malicious data meant to exploit the secure bio identify object. And then we feed the small object that's been tampered with to secure bio identify. And now we can exploit our Stack Overflow. So that's pretty cool. And for like, to give more like details about exploitation, as I said, there is no ASLR, so we can just, you know, wrap to do like, you know, what we want. To do that, I used some IDA script to locate, you know, like cool-looking chunk of codes, you know, like gadgets. And mostly, you know, branch, pop, PC, and, you know, whatever instruction would be useful for me. And just to give an idea, that's what it looks like in practice, you know, just using getDisasm in IDA to, you know, get the instruction and search for whatever strings that I was, you know, like the kind of gadget I was looking for. And plus, like, you know, some helping function to just get like the last few lines of code. And in practice, that's what would be outputted by the script, which is looks like, you know, oh, here it's called memcopy, and it's going to, you know, pop some registers, pop PC. So, and I do a bunch of that until I can stitch together like enough, you know, gadgets to copy a payload in a good location that I can execute. And for that, you know, as I mentioned before, there is some memory regions that are like mapped read, write, execute, and I found them like basically while reversing the firmware, like when the firmware starts, even if it does execution in place on the flash, I'm assuming it's kind of slower than like RAM, so it's going to copy some chunk of driver code into some memory regions that are meant to be executed, and I was just like, well, I'm just going to hope that there is, you know, empty space after that that's still like in the maps, you know, read, write, execute region, and that's not important for anything, and put my payload there. And that actually worked. And so basically now we can execute code, which is nice. But, you know, what do we want to do? There's like a few ideas that are cool. One that I thought was interesting is we can, if we want, return, like execute any code on the application firmware and make it return data back to our user land. So the way to do that, you run the exploit, and then you just write data inside, like a chunk of the large object we had allocated, and then we can retrieve that data using cv-get object. And with that, we can dump the RAM, we can dump the boot ROM, we can do a lot of stuff. But also there is a function called SOTP read key, which is used internally by the firmware to retrieve keys that are stored in the fuse of the chip. And we can call that ourselves now and exfiltrate keys that are for our chip, which sounds pretty fun. The other thing we can do that I won't go into too much detail today is we can also patch function pointers in memory. And this way we could hook or backdoor certain functions. And that was kind of like a baby step towards firmware modification. But I'm not going to talk about it more today because we'll have a better way of doing that kind of stuff. So first demo, I'm going to show how we can leak the keys. So yeah, let's go. So in that situation, it's a recorded video, obviously. From my laptop, I locate existing sessions because the system was in use. Forge a session, free it, called exploit secure bioidentify to call SOTP read key. And actually, I do that twice. And here we've leaked like 2 keys from the device, like an HMAC key and an AS key. And those are like for only the device I had, so I can put them on screen. It's like every device it's going to be different. So that's cool. But now you should be like keys. Like what are those keys, right? So it turns out there are like 7 OTP key slots. So OTP is like the one-time programming fuse. And 2 of them are used by like an AS and HMAC key that are used to secure the flash and also encrypt the secure code descriptor that I was mentioning earlier in the presentation. Then the secure code descriptor itself contains keys, once you decrypt it. One is the ERISA key that's used during firmware updates to check the signature of the update you're trying to do. And then there's also the AS and HMAC key that are used for the execution in place. And those are regenerated every time you do a firmware update. And finally, you have the hard-coded default keys that I mentioned earlier. And those are actually used when the SCD is missing. And now you'd be like, okay, how do you lose that secure code descriptor? Turns out there is a perfectly legitimate file called the clear_scd.bin that's used during firmware updates to force a reboot into the secure boot image. And basically the idea is during the update process, that file gets flashed over the legitimate SCD using CV flash update. Then they reboot the board, and the secure boot image is trying to load the SCD, and it's just see junk and stops and be like, okay, I'm going to wait for more commands. But here the thing that's crazy is literally we have an arbitrary flash write by design. Why is I did it that way? I don't know. But to be fair, normally all the flash is encrypted, so even if you can flash junk data on it, that's not going to help you. Not only it's encrypted, but also HMAC'd, so normally you shouldn't be able to do anything with that. But we just leak the keys that protect that mechanism. So now we can flash any data we want on the flash and make it valid. So that kind of begs the questions of how secure is the whole boot process now that we can tamper with the flash in some interesting ways. So to go back to the secure boot diagram, really the way it works is the boot ROM will verify the SBI, and the SBI will load the keys, the kind that we can leak, to decrypt the secure code descriptor, and those keys will be used to fed the execution in place engine and start the application firmware. But really the key in this diagram is there is no signature check of the application firmware at boot. So the whole security of that stuff really depends on that being secure and that being secure. And we've seen that we can leak those and tamper with those. So it looks a lot like that we could step towards firmware modification. So in theory, we can dump the device keys. We've just done that. Retrieve the secure code descriptor and decrypt it. We've done it. And then the more complicated step is we could retrieve the execution in place keys and forge our own blob of data and try to reflash that. But it's going to happen while we're executing the code, and it's a great way to just trash your system. Instead, what we can do is forge our own secure code descriptor that will contain our own RSA public key, and that one that we have the associated private key, and then we can forge our own firmware update for our own device, sign that with our own key, and feed it to the system, and that should work. So now, did it work? No. So turns out I messed up the endianness of the secure code descriptor, and I flashed kind of the bytes in the wrong order, and the whole thing just stopped working. And here you can see a Flash programmer trying to flash a non-good flash blobs, encrypted flash blobs onto the thing to restore it. When I did that, I tried again with the proper endianness, and the second time it worked. So here you can see the USB description of the device to Windows says control pwned, because I'm 12 and it's oh, hack the planet, and so yeah, the application firmware was actually modified, and that one will persist, after reboot, even if you install Windows, it will stay modified, because that has nothing to do with Windows. So technically, you can make your own permanent implant if you wanted to. It's pretty fun, but can we do more? So the board is called USH for Unified Secure Hub, but now we've shown that it's not that secure anymore. So what can we do with it? So one of the functions in the firmware is called CV fingerprint identify, and it's used when you try to log in with the fingerprint reader. Windows Hello is going to, through various, glue code or whatever, ask the firmware, look at the finger on your fingerprint sensor. Does it match any of the non-recorded user templates that you have? And because the check is done in the firmware, we can modify. What if we were can it always say yes, you're the right person? So I was let's just patch the function to say true all the time. Sorry, true all the time. And so second demo, in that situation, I flashed the firmware of the control rod firmware to just accept any finger. And here you have a plastic finger. I got DEFCON 2 years ago for some reason, and I taped a piece of green onion on it just because I needed something organic to trigger the sensor of the fingerprint. And we're going to see what happened when we put it on the reader. So you see, whoop, unlock. Thank you. So yeah, with that we can see we can bypass the login screen, assuming it's set up to accept fingerprints, which is not great. But the question is can we do more? What's is there more fun stuff we can do? And yes, we can try to target Windows stuff now. There's no SLR on the Windows side. Maybe we can mess with it. But before we go there, I just want to give some ideas of the communication. Oh, shit, sorry. The communication between the firmware and the host. So the idea is when you send a CV command, the host is going to prepare the arguments. This is kind of TLV type of thing. And for instance, and that one informs how the data is going to be decapsulated later on. So in that case, that first one is just going to be the data is just a raw buffer, just copy it into whatever buffer you provide. While this one here, the number 2, is going to be oh, actually, when you decapsulate the data, you're going to split it in 2 arguments. The first one is going to be the size of the data, and the second is going to be the data itself. Just to give an idea of the potential it is. I don't know why it's so complicated, but that's the way it's set up. Then what happens is the host going to prepare arguments for both direction of the communication. The data is going to send to the firmware, but also prepare the argument it expects to retrieve from the firmware. So destination buffer, allocating buffers and so on. Then the whole thing gets serialized. You send the CV command. And upon return, the data gets deserialized and then decapsulated according to whatever specification was set up. In practice, for CV get random, on the host side, you can see here you initialize all the parameters. You call the function. You can see here it's CV get random, And upon return, you decapsulate the stuff. It's cool, nothing too crazy. But when you look at the way it's done on the firmware side, before calling the cv-get-random command, you can see it's redefining the encapsulation type of the output data is going to be sent back, and the size, and so on. So I was like, what if we modify that, Because it turns out the host is going to trust that new serialization that's sent back from the firmware. And with that, you can basically have like overflow and type confusion, like if you change the encapsulation type in the firmware or the size of data that's being returned, while processing the data back from the firmware, the host is just going to like get messed up. Practically, like what I did was backdooring cv-get-random with this ID. Like let's look at the decapsulation. Here it's expecting like there was like the type number 2 that split the data into a size and a buffer. You have the size here, which is like an integer on the stack, and the buffer that will receive the data. But if on the firmware side we change the decapsulation type to like a raw buffer, what's going to happen is this argument, which is an integer, is going to be confused with a buffer and is just going to be filled with the data sent. So with that, we can backdoor the cv-get-random command, so that if you request a specific magic size of random data, instead of returning that, it's going to return like a malicious payload that gets decapsulated the wrong way to exploit, to overflow that blen variable. And as I said, it's going to treat blen as a buffer and overflow it and provide like whatever shellcode we want. So to give an idea, I made like a little like toy program on that side that's pretty much just calling cv-get-random. And if you have no command line argument, it just calls like normally. And if you put any command line argument on that side, it will call cv-get-random with that backdoored value that will trigger like the exploit. So that looks like that. Like first I just show like, the vulnerable function. I don't know if you guys can see. And it's just like really straight out calling cv-get-random. It runs the first time, just calling like normally, and I'm going to do a second time, still normally. It's like you see it returns just like random data. But the third time I'm like calling with a special argument that triggers the backdoor that sends a shellcode, and boom, we pop calced, which is cool. But yeah, to just give like some challenges here. That exploit, use hard-coded offsets, for like the Windows version I have and so on. So, if you were to try to go to the real like implant that survive Windows like reinstall, you'd have to accommodate for, figure out like the proper Windows version and so on. And also, not only it corrupts the stack, but it also corrupts the heap, on the Windows side because, the arguments are processed multiple times. And if you run that with a debugger, it's going to fail every time. So I was like really sad because I thought like my process was broken. But if you run it without a debugger, like it's going to work like sometimes, and sometimes Windows is going to pick up the corruption and fail. But 20% of the time it works. And a cool trick I used was to also backdoor a cv-get version, like the thing that we return a big like blob of data that doesn't really matter. And the idea here was, on the Windows side, you start doing some rob chain, but to map a memory region like read-write execute, so you can do more start your shellcode or whatever. And I made it so that calling cv-get version would return or shellcode, if we've been in that like exploitation stage. And to get that, I patched, stuff in the firmware that just looked like, useless code. And whether or not, I want to call the patch or just the normal code, I would just check if, whatever condition is met, I would, do the real thing, otherwise I would jump to the malicious payload. And in practice, hopefully you guys can see a little, the process is just like, to patch the firmware, you overwrite the beginning of the function with, load an address that will have like the actual payload you want to mess with, save the instruction you've overwritten, and in your payload, you will be like, okay, restore like the normal execution flow or execute the thing. And like, for instance, here for like backdooring the CVGet version, that's kind of look like that, where it would load some global variable that says like use the backdoor or don't use the backdoor. And here I would like patch later on like the instruction that I removed to get that. So just to give an idea of the way it works. But yeah, so it's cool, you know, we hacked our own toy binary, but can we do something better? Let's, you know, and we've seen like the like system services, so let's go for it. The challenge is like, you know, we want something that runs with high privileges, that use the control vault DLL because they have no SLR and no stack cookie. And some targets, you have like Broadcom services, third-party application, but I couldn't find any. And Windows Hello. We've seen, you know, Hello interface with the control vault, and you have those DLLs for that. So I spent so much time looking for all the potential function that could be like, that could be exploited in that way. I'm really sad because it's like taking forever and it's a pain in the ass. But eventually I found that sweet spot. It was like the Broadcom storage adapter function, DLL, that is used by Windows Hello to interface with the fingerprint. And it has this function here that will take a handle to an object, check if the object exists or something, and load the header of the object, you know, onto a stack variable. And that stack variable somehow is past the end of the frame of the function. And if we look at the parent frame, it's, you know, like in the parent frame, you can see there is no stack cookie or anything. So if we can overflow that header, we can overflow the return address and start like a rogue chain. And basically, like that function is that function here is a wrapper to CVGet object, and we can, you know, patch CVGet object and overflow that function the same way we did for CVGet random. And so in practice, we can, you know, overflow that, or we can mess with that command to overflow that object and, you know, take control of the execution. And in practice, to trigger that, that DLL is loaded by the Windows biometric service to implement the fingerprint handling, and you can reach the function I was pointing at via kind of like a IO control-like interface that any user can call. And so the call stacks look like that. You know, that is reachable from like a user. We'll call that function, and eventually got that we can, you know, tamper with. So in practice, we can overflow the object header and corrupt the parent stack. The way it looks like, I already deployed a firmware, like a modified firmware that will provide the shellcode to start Netcat. And on that side, you have the Windows biometric service that will get exploited. And just to trigger that vulnerability, we will call into the Windows biometric service with that magic handle that we've used to backdoor the CVGet object command that will provide, you know, like an exploitation payload as opposed to like the legitimate object you would be requesting. In practice, it looks like that. Just to highlight the command, that's the script to just, you know, trigger the function with the arbitrary handle. We run that. It's spawning like Netcat here. And then we can just connect to our local, to that Netcat server we just spawned. And if we look, now we have a system shell. So yeah, with that, we were able to hack, you know, an actual thing, not a toy binary. So far, what we've done: code execution of the application firmware, permanent modification of the firmware, bypass of the login screen, and system privilege. Can we do more? So yes, last thing, I'm running out of time anyway. The control vault device is a internal USB device. And I was like, could you make it like an external USB? And so this contraption here is just like splitting out the ribbon cable that should go into your motherboard into a bunch of power cable, 3 and 5 volts, and a USB adapter. And what you can do is basically connect a board to like a USB connector. And when you plug it into the machine, it will show up as you know, a new control vault device. And that new control vault device, you can also interact with it the same way I was doing before. So that's nice. But basically what that means is now, like all of us talking about was assuming, you know, a malicious user or compromised user, but now, like, if you just leave your laptop unattended, you can open it, connect to that ribbon cable, and hack the board that way. So it becomes also a physical attack. So as a summary, like, there's like 2 attack scenarios that are interesting. Post-compromise, Like, the user gets, popped. Threat actor could modify the firmware of that board and then, compromise Windows. And the physical attacker could, open the device, remove the battery, connect to the board, modify the firmware, and then bypass the fingerprints or compromise Windows. So overall, like the findings, Dell released an advisory in June. Most of those reports are on the Talos website. Bunch of CVEs. There's more to come. There was meant to come like next week, but it's going to be in a month. But FYI. And the two write-ups, like a high-level overview. That's probably not that interesting, but then technical. The high-level overview that's like just high level, and then the technical deep dive that is more details on that. And yeah, so I think I'm out of time. So just. Yeah, firmware security is not a new topic, but I think it's really important for us to understand what's running on our machines, especially when you have this mysterious piece of hardware that's been there for like 15 years, undocumented, no information. Like, I think it's our job to like audit those, understand how they work, and be a little more like inquisitive about it. So thank you. I'm out of time for questions, but you can find me later on. And yeah, thank you.